Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 3.2 from your textbook and discussing some last few properties of the determinant. Before we get into those properties though, we're going to quickly go back over one of the theorems that we discussed from the last lecture, which was the theorem that sort of tied together invertibility of a matrix and the determinant of a matrix. So that theorem is stated right here. This theorem just said that if n is an n by n matrix, then A is invertible if and only if its determinant is non-zero. So remember, since this is an if and only if, you get actually four different directions from this theorem. It tells you that if A is invertible, then its determinant is non-zero. It tells you if a matrix's determinant is non-zero, then it is invertible. It tells you that if a matrix is not invertible, then its determinant will be zero. And it tells you if the matrix has a determinant that is zero, then it is automatically not invertible. So you get actually four different statements from this theorem here. So let's tie this in a little bit with discussing like solution sets of systems of equations through a quick example here. So we did something like this a few videos ago when we were learning about rank and how that relates to solution sets. So what we're going to try to do here is we're going to describe the solution set of each of the following systems as sort of fully as possible. And for all of these, we're going to assume that B is not equal to 0. So in this first one, we have AX equals B, where A is a 5 by 5 matrix. So this means that this system has 5 equations and 5 unknowns. And we know that the determinant of A is equal to 6. So let's think about what we can say about this. Since the determinant of A is equal to 6, which is not 0, that means A is invertible. And if you think about what that means, right, we know how that connects to sort of rank. If A is invertible, then its rank is full. So that means rank of A is equal to 5. Well, that means that when you look at this system of equations and you look at A augmented, there is no potential that A augmented is going to have a larger rank than this because A augmented would be 5 by 6, so its maximum rank would also be 5. So we can say that rank of A is going to equal rank of A augmented, which implies that there are going to be solutions. Since there were 5 variables and the rank of A must be 5 here, we actually know it's going to be a unique solution. And we can actually talk a little bit about that unique solution. Since A is invertible, that unique solution is X equals A inverse B. So in this situation, right, if the determinant is non-zero, that means it is invertible, which means it has full rank, which means it has unique solution, and we actually know what that unique solution looks like. It's the inverse times whatever the set of constants was supposed to be. All right. Did it matter that the determinant was 6? Not really. As long as this was a non-zero value, all of this logic would apply here. All right, let's look at the next one. AX equals 0, so this is a homogeneous system, AX equals 0, where A is 7 by 7 and the determinant of A is 0. So determinant A equals 0 implies A is not invertible. So what does that tell us about the rank of A? That tells us that the rank of A must be strictly less than 7. In other words, it does not have full rank. All right. Is it possible, though, that the rank of A augmented is going to be larger than this rank? Well, we know that that's impossible because this is homogeneous, right? Now, it could have been possible because the rank is smaller, but since this is a homogeneous system, augmenting the matrix will not actually cause there to be any additional rank. So we know this is a homogeneous system, which implies that rank of A must equal rank of A augmented, which means that there must be solutions. Well, are there going to be unique solution, infinite solutions? Well, we know that the rank is less than 7, which means it's less than the number of variables. So we know it's going to be infinite solutions. And how many free sort of parameters? Well, we can't really be too specific. We know it's going to be 7 minus whatever the rank of A is. So with 7 minus rank of A, free parameters. And we know that this will be at least one free parameter, which is why we're safe in saying infinite solutions, because rank of A must be less than 7, because the determinant is 0 here. Okay, let's try that again, right? We've got AX equals B, where A is 4 by 4, and the determinant is 0. So once again, determinant A equals 0 implies that A is not invertible, which implies that rank of A, in this case, must be less than 4. It must have less than full rank. Now, is this a homogeneous system? Well, no. We're told to assume that B is non-zero here, so this is going to be non-homogeneous, which means that there is the potential that the rank of A augmented is larger. So we actually have two cases. If rank of A augmented is larger than rank of A, which is a possibility here, then this means there will be no solutions. If rank of A augmented equals rank of A, then there will be solutions, and it'll actually be infinite solutions with 4 minus the rank of A free parameters. How do we know that there's going to be infinite solutions? Well, we know the rank of A must be less than 4 because it's non-invertible since its determinant is 0. So there's got to be at least some lower rank, so there's going to be at least one free parameter, meaning that it's going to be infinite solutions. Notice, though, that this guy does have the potential for no solutions because he is non-homogeneous. All right, last one down here, right? We've got AX equals 0. A is 6 by 6, and the determinant of A is -1. Again, we don't really care that it's -1. All we care about is that that's non-zero, which means A is invertible, which means that the rank of A in this guy must be 6. He must have full rank. All right, if we take that, then we can say that we can sort of put this stuff together a little bit. We can say if, we don't need an if here, sorry. We can say that since this guy is a homogeneous system, right, we know that rank of A equals rank of A augmented, and we know that there's only going to be one solution. It's going to be unique in this case. How do we know it's unique? Well, we know that the rank of A is 6, and we know that there's 6 variables, so it's got to have a unique solution. And we can actually say what that unique solution is. We can say it's X. Well, you would say A inverse B, but you don't even need to really say A inverse B because that B is 0 here. So the unique solution is X equals 0. So this just gives you guys sort of a little bit of an exploration about solution sets and the determinant. Notice that the determinant basically allows us to tell if something is invertible or non-invertible, and then that gives us a tremendous amount of information. Keep in mind that this only would work when you have square systems like this, because concepts like the determinant and invertibility only apply to those square sort of systems or square matrices. All right. We proved a couple properties of the determinant in the last video. We also mentioned a couple others. In the next sort of thing that we want to look at here is a summary of all the properties of the determinant. We're not going to really prove anymore because I think you guys have seen enough proofs using the definition of the determinant, but we are going to just briefly discuss these properties. So these are sort of 10 properties of the determinant. These are also listed in your textbook. Let's just go over them sort of one by one. So properties 1 through 3 here all sort of deal with elementary row operations. These are the ones we stated in the last video. So P1 says that if B is formed from A by interchanging two rows, then the determinant of B is negative determinant of A. We actually proved that completely in the last lecture. We also proved P2, if B is formed from A by multiplying one row by a non-zero scalar K, then determinant of B is K determinant of A. So we actually proved that guy as well. P3 we stated in the last lecture, but we didn't prove it. You can see the proof in your textbook though. If B is formed from A by adding a multiple of one row to a different row, then determinant of B is determinant of A. And we actually did prove this guy as well. If B is equal to Ka, if you multiply the entire matrix by a scalar, then the determinant of B is K to the n determinant of A. And remember, this guy is proved from using property 2, just repeating it n times since there are n rows. Then we've got some new properties here. We're going to just state these, and if you want to see proofs of them, formal proofs, you can go ahead and look in your textbook. But property 5 says that the determinant of the transpose is the determinant of the original matrix. So if you take the determinant of a matrix, if you take the transpose of a matrix, it does not change the determinant. So that's property 5 there. Property 6 is maybe one of the weirdest ones. We don't actually end up using it very frequently, but we should state it. So what this basically says is if you've got R1, R2 down to Rn are the rows of matrix A. And then we're going to suppose matrix B has rows R1, R2 down to Rn. The only thing it differs from matrix A is in row K, where it has BK as its row. And matrix C has all the same rows, R1, R2 down to Rn, except in that kth row it has CK. And we're going to suppose that RK, that kth row of the matrix A, is the sum of BK and CK. If that is the case, then the determinant of A is the determinant of B plus the determinant of C. So what this sort of tells you is that determinants definitely do not distribute over matrix addition. They instead distribute over this weird form of addition where you only add one row and all other rows remain the same. Now, I sort of said that we don't use this that frequently, but I do think it's the most complex to sort of read. So I am just going to give you guys a quick sort of example to think about here, right? And you can also see why we might potentially be interested in using it. So suppose you're trying to calculate this determinant like 2, 0, 0, 1, 2, 1, 0, 0, 5. Okay. If you were going to try to calculate that determinant, you guys know some ways you could do that. You could, for example, flip this guy up into row 1, move this guy down into row 2, and then sort of clear out anything down here, and then hopefully you'd have it in sort of upper triangular or diagonal form and be able to get the determinant pretty quickly. What this property 6 is sort of saying, right, is that you can sort of split this into a sum of two determinants. What you can do is, let's say you go ahead and leave row 1 alone, so 2, 0, 0, and you leave row 3 alone, 0, 0, 5. And you do the same thing over here. Then, this will be true if you choose two rows here and here that sum up to this. So I could choose, for example, like 1, 1, 0 and 0, 1, 1. Because if you notice, 1, 1, 0 plus 0, 1, 1 is going to add up to 1, 2, 1. And then this property tells me that this determinant here is equal to the sum of these two determinants. Why might that be useful? Well, you guys might notice that this guy is lower triangular, so I can just go ahead and do the product here of those diagonal elements. And this guy is upper triangular, so I could just do the product there, and I could very quickly get that this is 10 plus 10, which is equal to 20. So I would get that the determinant of this is equal to 20. And if you go back and you actually try this using the old techniques, you would find that you also find that that is 20. Now, is this like a common thing? Is this really useful? I don't know. This was pretty lucky, and I designed this example ahead of time so you guys could sort of see this trick. I don't really find that this happens very much in practice, but it's a nice property of the determinant. All right, let's go back to talking about the other properties here, P7 through P10. So P7 is a very useful one, right? This can speed up some of your computations. If you're ever calculating the determinant of a matrix, and you find that the matrix has a 0 row or 0 column, then you immediately know that the determinant of A is 0. This guy, we're not going to prove formally, but we can give a very quick verbal proof. This should make a lot of sense considering that when you do the definition of the determinant, you select one element every time from every row and column. If there's a 0 row or a 0 column, every time you pick something from that row or that column, you're always going to put a 0 into the product, and that's going to make the term 0. And then the determinant is going to be the sum of all those zeros, which is going to be 0. P8 is directly from P7. It's basically just restating P7. It says if you have two rows or columns that are scalar multiples of one another, then you immediately know that the determinant is 0. Why is this true? Well, if you have two rows that are scalar multiples of one another, then you can simply use the elementary row operation to take one of those rows away from the other, and you will build a 0 row. And since elementary row operations don't change the determinant except for a scalar multiple, then if you get that it's 0, a scalar multiple of 0 will also be 0. So that should make sense there. Property 9 is incredibly important, so this guy probably should deserve the sort of stars here. This says that the determinant does distribute over matrix multiplication. So the determinant of AB is equal to the determinant of A times the determinant of B. So you can take the determinant of a product or do it as the product of the determinants. Very, very important. Finally, P10 says that if A is invertible, then the determinant of A inverse is 1 over the determinant of A. And that should make sense. Proving P10 is not hard if you use P9. You know that A inverse has to equal the identity. You take the determinant on both sides and you can prove this property. So a lot of these properties are sort of proven by other properties. If you want to see all those proofs sort of formally done, go ahead and check out your textbook, and they do go through each of those. For us, though, we're going to use the remainder of this video to look at some examples of using these properties to calculate determinants and just think more about what they're sort of saying here. So let's go ahead and take a look at this example here. So we've got 3 matrices here, A, B, and C. They are all 5 by 5 matrices, and we know that the determinant of A is 3, the determinant of B is -2, and the determinant of C is 4. So we don't know what the matrices look like, but we do know their determinants. And we want to try to calculate the determinants of all these things. Notice that in some of these later ones, you'll see like the inverse floating around. Remember, the inverse makes sense because all of these determinants are non-zero, which means that they must have inverses. So let's think about this guy first. We wanted to calculate the determinant of 2A. So what do we know about this? Well, if we go back, we can see that we have property 4 that says the determinant of a scalar times a matrix is the scalar to the nth power times the determinant. So in this case, we would say that this is 2 to the, well, they're 5 by 5 matrices, so you're multiplying 5 rows by 2. So you get 2 to the 5th times the determinant of A, which of course would be 32 times 3. So we know that this matrix would have a determinant of 96. So the determinant of 2A, the matrix where you double every element in A, would be 96. Okay, let's think about this guy, determinant of AB transpose. What can we say about this? Well, we can go back here. We can use that property 9 to say the determinant of a product is the product of the determinants. So we can say that this is determinant A times determinant B transpose. Then we can say, what can we say about determinant of B transpose? Well, we know that the determinant of the transpose is the determinant of the original matrix. So we can say that that is determinant A, determinant B. And then we can just plug in 3 times -2. That looks like that guy would have a determinant of -6. Okay, let's try this guy here. We've got determinant negative B inverse. So let's pull that -1 out first. That would be -1, and we'd have that on 5 different rows. So -1 to the 5th, determinant B inverse. Now, of course, -1 to the 5th, we can just simplify that. That's negative determinant B inverse. What do we know about the determinant of B inverse? Well, we can go back over here. Determinant of B inverse, or of any matrices inverse, is 1 over the determinant of that matrix. So this would be -1 over the determinant of B. And then we can see right there that the determinant of B is -2. So simplifying that, we should get 1/2. And of course, that's because we would get double negatives, negative, and -2. So positive 1/2 as the determinant there. All right. Maybe most complicated here, we've got this messy determinant. We wanted to get the determinant of A times the inverse of B transpose C inverse. So we can do this in a lot of ways, but let's just unpack piece by piece. Let's first think about this as a product of A and this crazy thing. So if we do that, we can write that as the determinant of A times the determinant of B transpose C inverse. Okay. Now we can work on this stuff in here. If we want, we can say that the determinant of this inverse is just 1 over the determinant of what we're inverting. So we can say that that's determinant A times 1 over the determinant of B transpose C inverse. Because we know that the determinant of an inverse is 1 over the determinant of the original stuff. Okay, what can we say about this? Well, now this is a product, so we can split that up. So we can say that that's determinant A times 1 over determinant B transpose, determinant of C inverse, right? Because the determinant of a product is the product of the determinants. Then we can say, okay, determinant B transpose, we know that's determinant B, and this guy is going to be 1 over the determinant of C. So we get determinant A, 1 over determinant B, 1 over determinant C. So we plug all that stuff in. Determinant A, well, that I believe was 3, so we get 3 times 1 over. Determinant B, -2, and then 1 over 4. So that looks like 3 times 1 over -1/2. And if we do that, looks like we should get -6. So the determinant of this crazy matrix would be -6 there. Could you do this in a different way? Sure, you could use properties of the inverse as sort of an alternate method. We'll just pop this over here, right? Alternately, we could have simplified inside first. So we had this, and we know that the inverse distributes over matrix multiplication by reversing. So we could have said that this is the determinant of A, and then C inverse inverse, B transpose inverse. And then we could have said, well, C inverse inverse is just C. So we could have said that this is the determinant of A, C, B transpose inverse. And then we could have done the same breakup of this and these two, and then break these two up after that. So again, there's often several ways to sort of use the properties and manipulate these different things. So these are just a couple examples for you guys to see how to use these different properties to calculate determinants, even when you don't have access to the actual matrices or the elements themselves. Let's take a look at one more example, sort of similar to that, and trying to just again give us some practice using these properties. So for this one, right, we're going to consider this matrix A here. This matrix just has these unknown elements A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. And then we've got this matrix B here, which looks sort of crazy. We've got 2I, -E, A, M, 2J plus 2I, -F minus E, B plus A, N plus M, 2K, -G, C, O, 2L, -H, D, P. We're going to assume that the determinant of this is equal to 3, and we want to try to calculate the determinant of B. Okay. So let's go ahead and see if we can do this by starting with this matrix and trying to use different operations to get to this matrix. And we know how those different operations, not necessarily just elementary row operations, but things like the transpose and stuff like that, how those affect the determinant. So let's go ahead and start with this. So we'll keep sort of track of this. We've got this square matrix, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. And we know that this guy, determinant here, we don't need to write out determinant, that'll just make things messy. We know that this determinant here is 3. Okay, so let's look ahead and sort of see things that we need. We can see that things like E, F, G, and H all got negated. So it might be a good idea to go ahead and multiply this row by -1. We can also see that things like I and J and K and L all got multiplied by 2. And I, J, K, and L are all in row 3. So let's start with a couple elementary row operations. Let's take R2 and replace it with -R2. And let's take row 3 and replace it with 2 row 3. Now, we know that that'll cause the determinant to be multiplied by -1, and this will cause it to be multiplied by 2. So we'll multiply this guy by -2, and we know that this matrix, A, B, C, D, -E, -F, -G, -H, 2I, 2J, 2K, 2L, and M, N, O, P. Well, I'm trying to do that as a determinant there. That guy has determinant -6 because we multiplied by -1 and we multiplied by 2. All right. What else do we see that we need here? Well, we can also sort of see that eventually we're probably going to need to apply a transpose because if you notice, things like you don't have a row up here of A, B, C, D. It looks like you more have a column of A, B, C, D. So it looks like we're going to, at some point, going to need to do a transpose. Now, you will notice, though, it does look like there were some additions that happened here. And you'll notice that that's sort of like A and then B plus A. There's no way in our current thing where we could add B and A together because they're not in the same, they're in the same row. So there's no elementary row operation that would allow us to do that. So maybe it's a good idea to go ahead and do the transpose here. So let's see if we can go ahead, do the transpose and see what that looks like. So we're going to transpose now. So let's go ahead and do that. That would be A, B, C, D, negative E, negative F, negative G, negative H. Well, that looks a little rough, though, because that looks like that A, B, C, D is going to be in the wrong spot, if you think about it. So maybe before we do that, since we want those A, B, C, Ds to end up in the third column, maybe we should interchange these two rows first. So let's go back and do that. And there's no harm in sort of recognizing that maybe we need to do that first. So let's go ahead and do that. All right. And notice that does definitely correspond to also getting these guys in the right position, right? We'd sort of like them to eventually become the first column. So let's interchange row 1 and row 2, or row 1 and row 3, excuse me. So let's interchange row 1 and row 3. So if we do that, we're going to get 2i, 2j, 2k, 2l, negative e, negative f, negative g, negative h, a, b, c, d, m, n, o, p. And, of course, we interchange two rows, so, of course, we know that that negates the determinant. So this guy has determinant 6 now. All right, now we can go ahead and do the transpose. Now, the transpose is not an elementary row operation, but we do know what it does to the determinant. It doesn't change the determinant at all. So if we do that, we get 2i, 2j, 2k, 2l, negative e, negative f, negative g, negative h, and then A, B, C, D, and then M, N, O, P. Okay, so that looks pretty good. We're almost to what we have here. Last thing we sort of need to do is we'd like to have this 2i, this negative e, this a, and this m. So we will add row 1 onto row 2. And of course, when we did this transpose, it didn't change the determinant at all. So now let's go ahead and do one more thing. Let's take row 2 and replace it with row 2 plus row 1. This sort of elementary row operation obviously doesn't change determinant. So when we do that, we should get 2i negative e, a, m, 2j plus 2i, minus f minus e, b plus a, n plus m, 2k negative g, c, o, 2l negative h, dp, and of course that guy would also have determinant, let's just slide that down there, that guy would also have determinant 6. So this guy right here does match our matrix B. Everything is the same here. So we can say that the determinant of B in this case is 6. So even though we don't know what these elements are, just these operations here dictate that the determinant of B must be 6. So again, these examples here are mostly just to get you guys more practice using and understanding what these properties of the determinant really mean. All right, let's talk about one last thing. Let's go back to a sort of a special type of matrice that we introduced a while back and see what we can say about its determinant. So as our sort of final thing in here, let's recall this definition. We said that an invertible square matrix is said to be orthogonal if its inverse is equal to its transpose. Let's go ahead and prove that if A is orthogonal, then the determinant of A is either plus or minus 1. So let's see if we can do this. So we get to assume A is orthogonal, and we need to show the determinant of A is plus or minus 1. So since we assume A is orthogonal, we get to assume this identity. We get to assume that A inverse equals A transpose. Now, we need to show something about the determinant, so maybe we can apply the determinant on both sides here. So the determinant of A inverse must equal the determinant of A transpose. Why? Well, if these two things are equal as matrices, then they must have the same determinant. Okay, what can we say about these? Well, we know some properties. We know this is 1 over the determinant of A. And we know this over here Determinant of A transpose is just determinant of A. So we know this is determinant of A. But then this is something we can solve, right? We can multiply this over onto the other side and get 1 equals the determinant of A squared. And of course that means the determinant of A is equal to plus or minus 1. And that's exactly what we wanted to prove. So now what we basically did here, and this is something that's very common in linear algebra as a branch of mathematics, is we gave this definition of sort of a property of it's a sort of important type of matrix, these orthogonal ones that have this idea that their inverse is their transpose. And now we know that they also have this property, that their determinant must be plus or minus 1. In other words, we've sort of learned that by having this property, they automatically also have this property. We've got one last sort of video for Chapter 3. We're going to introduce Section 3.3 in the next one. Until then, well, hope you guys all take care.